in the last class we learned about atom. We learned what inside the atom. We learned about nucleus. We learned about electron, proton, and neutron. And also we know that the atom mostly is empty space. And also we know that different kind of atom make up different element in periodic table. So today we will learn about the periodic table. One of the trend, what is their trend, and also what is inside the periodic table. So if you look at the periodic table, this thing, okay, so you see some numbers there. Okay, there are some numbers there. So you can see 1, 1, and 1.008, and then 8, 2, 6, and then 15.999. Certain periodic table doesn't have this. Okay, certain periodic table doesn't have the small numbers on the right, but have a numbers here. This number denote the what we call the atomic number. Okay, so for example, the atom number 1 is basically helium and so on. 8 is for oxygen and so on. So that is number of proton. This number of proton inside the nucleus, and number of proton must be sort of like the number of proton and number of electron should be sort of like equal in order to make the charge of the atom neutral. So that's why you see here, this is the what we call the number of electron. If you look here, the number here 1, 1, 8, and 6, 2 is 8. It's always the same. Okay, because if this is not the same, then the atom become ions. So periodic table is basically the atom only, the element, not the ions. So here and here must be equal. Okay, so that is basically the electronic configuration lah. Number of electron must be the same of this atomic number. And then at the bottom there, you will see some numbers with some decimal, 1.008 and so on. So this denote the atomic mass. Okay. The question now, what is the unit? Because we know mass is a certain what we call the one of the SI unit lah. But what is the unit for these numbers here? We know it's a mass, but what is the unit here? What is the unit here? 1.008. What is the unit there? AMU? And then anyone else? Okay. Anyone? What's the unit? Unit. The unit, Nasha? What's the unit? AMU. Okay. But then some people said that this is mass. So AMU, is it a mass? It's a unit. AMU is unit. Okay, so the numbers here can be both. Can be both AMU or mass. So here, the unit for here is gram per mole. Whenever you read the periodic table, this thing is more adequately referenced as a gram per mole rather than AMU. Because AMU, we will discuss later, is more about unit. And the unit must be whole number. I will discuss AMU later, but for time being, we look at this gram per mole. So the mass here is gram per mole. You cannot say this 1.008 is gram, or this 15.999 is in gram. It must be gram per mole. For example, if you say this is gram, 50 gram of oxygen, you really, the one atom of oxygen is not really 15 gram. It must be have a mole there. So it's sort of like what we call something inside something. For example, gram inside the mole. For example, gram per mole, this thing. So the question now, what is mole? What is mole? What is mole? Measurement. What is mole? If you go to the interview after you finish your fourth year, you go to the job and then suddenly that job interviewee asks you, what is the mole? How do you answer that? What is the mole? What is the mole? Bonus mark. What is the mole?
Concentration.
Yeah, but what is concentration? What is mole? Concentration is concentration lah. For example, you have a dark coffee and a light coffee. You can say that different concentration. But what is mole? Mole is yes concentration, but what is actually mole? Yes. No, you need to raise your hand. What's your name? Izati. Okay. What's mole? Okay, mole of substance. But what is it? You need to go further. Go further. Because concentration also amount of substance. Carbon 12. Sorry, what you say?
The amount of substance of carbon 12.
Okay, so Rabi said the amount of substance in carbon 12. In carbon 12, there are electron, there are proton, they are neutron. So that's just an atom. So because inside the carbon-12 there are 6 proton, 6 neutron, and then 6 electron. That's it. There are nothing about the mole there in just carbon-12. You need to go further. What is mole? To measure how many. But what is that quantities? What is that? What is mole? What is Avogadro? Okay, we stop here lah. Okay, if I ask you, give me 1 dozen of apple, how much you will give me? Okay, why you know that? Yeah. If I ask you, give me 1 mole of apple, how much you will give me? So that is basically mole. It's a unit for quantity. This thing, I want this number. Okay. So 1 dozen of apple is 12 apple. 1 mole of apple is this much of apple, 6.02 blah 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 blah. Okay, so that's a lot of apple. So the question now, how much 1 more apple can occupy this? For example, this calculation lah. But this is not the bonus mark. I just need to go faster. So for example here, if people ask you, give me 1 mole of apple, you know that you need to give 6.02 times 10 to the power of 23 apple. So now, let's say the question asks you how much 1 mole of apple can occupy Earth's volume. This is engineering question lah, because they involve the calculation. So you know an apple is like a sphere. Apple is like a sphere. You give there, for example, apple diameter is 10 cm. Okay, so you know the volume for the sphere is what? It's 4/3 pi r3 lah. So this is volume of the sphere. So the volume of sphere is this. So you know the radius for this is 5 cm. So basically 4/3 pi and then 0.05, let's say we want to do in SI unit meter, times 3. So calculate that. Did I calculate or not? Anyone calculate that thing? 5.2 times 10 to the power of? -4. -4? Why it becomes small? -4? Okay. Okay, that's okay, because it's meter. Okay, because it's meter, because this cm meter is just like 100 times smaller than centimeter. So you get this. Okay, so that is basically the volume of 1 apple. If you want to have 1 mole of apple, let's say 1 mole of apple, let's say this apple, so it basically 6 times 10 to the power of 23 times 5.2 times 10 to the power of negative this meter lah. So basically 1 mole of apple, it will equivalent to 3.1 times 10 to the power of 20 meter cube. Okay, so basically it's just simply a calculation lah. Just I want to show you how to understand the mole lah. So this is the amount, the volume that is filled by 1 mole of apple. The question now, how much 1 mole of apple can occupy Earth's volume? So now the second, what we call the second conversion of the unit, you need to know how to convert 100,000 billion cubic kilometer to the meter, because that is meter, right? So you know the Earth is basically 1,000 billion cubic kilometer. So billion, the SI unit for billion is to the power of 9. So to the power of 9, and that is kilometer. Kilometer, what we call cube. That is the volume of our Earth lah. So now, because our mole of apple is in meter, and we are using kilometer here, we need to make sure the what we call the unit is consistent so that we can easily play around. Okay, so this thing, how to convert to meter? How much? It become what? It become what? Okay, 1,000 times the power of 12 what? Meter squared. This is wrong, because this km squared. 1 km, if you want to convert to meter, so you need to sort of like 1,000, because this is cube, so you have on km, this meter times 1 km, this is 1,000 meter times 1,000 meter divided by km, because there are 3 km, because to cancel the cube here, so you basically have 10 to the power of 9 here. 10 to the power of 9 here. So basically, The correct answer when you do all the stuff, you get this also wrong in what we call this 1000 10 to the power of 12 is this is basically 1 10 to the power of 12 km cube. Okay, so this convert become 1 10 to the power of 12 kilometer cube, and then to convert it into the meter, you get, because this 9 12, you get 1 times 10 to the power of 21, because it's meter. It's meter. So that is meter cube. Okay. So please make sure, many students, this is useful for any engineering course lah, because conversion of the unit is very important. So you need to make sure this is you are clear about this. Where is the madam? Okay. So that is basically the volume of the Earth. And if you compare with the volume of the apple here, 3.1 times 10 to the power of 20, you see, it seems that the difference is not much, because there is 20, there is 21. But if you divide them together, for example, 1 times 10 to the power of 21 divide by 3.1 times 10 to the power of 20, you will get times 100, because you want to find how many percent, so you get only 31%. Okay, so even though you see that this is the 1 mole of apple, this is basically 1 mole of apple. This is volume of Earth. Even though you see, this is mathematics, even though you see the difference between 21 and 20 is just like 1, but you need to prove it. So to see how much apple can fit in the volume of Earth, you divide lah. You divide and times 100, you can see how much percentage the apple can fill. And if you do that, you see that it's 31%. Okay, it's much less than you think lah. Okay, so you need to prove. When you do like calculation, you need to prove it. Okay, so sometimes you heard the people say that the volume, the water occupy 70% of Earth, right? That is on the surface. When people say water occupy 70%, that 70% is occupy the surface of the Earth. Surface of the volume, surface and volume is two different things. So the water only occupy the surface only, but you remember volume is including everything inside, the mantle, the crust, and so on. So the volume is much bigger than the surface. So when people say 70% of the Earth is covered by water, the word is covered, not the volume. So make sure you sort of like understand the difference between the volume and also the surface, because this thing will crop up again and again when we talk about nanotechnology later on. In the future lah, in the nano material later on, after the mid-sem. So I want you to be sort of adept with converting the unit and so on, especially the surface and the volume. Okay, so you can see that when people say 1 mole of apple is too much, it's a lot, even though it's 31% of the volume of the Earth seems small, but you see the Earth is big, right? So it's like, it's impractical to use mole for something big like apple. But if you do this thing for the something that is small, like is water molecule, which is something tiny, then the use of mole is useful. Okay, because you know that water molecule, you cannot even see it, but you know it's small. So how much 1 mole of water? If people ask you, give me 1 mole of water. Let's say you go, after this you go to the canteen, and then you want to be so, like what call, so nerd. You ask your friend, okay, give me 1 mole of water, and you tell, and then, yeah. How much 1 mole of water? This no bonus mark, but jawab lah. 1 mole of water, okay. Okay, 1 mole of water, yes, 6.02 times 10 to the power of 33. When I say 1 mole of water, H2O, meaning that there are 602 times 10 to the power of 33 water molecule. Meaning that this thing lah, there are this much of this. But then if I ask you, give me 1 mole of water, how much will you give me? How gram? How much of water? How milliliter of water you will give? If I say to 1 mole of water. This is the purpose of this thing. So you see in the bottom here, you can get this under hydrogen. There are this, for 1 mole you have 1, and this is 16. So H2O, if you look H2O, 1 mole of H2O in terms of gram per mole is basically, H is basically there are 1, I just round up the mass, molar mass, 1 gram per mole, 1 gram per mole times 2, because there are 2 H here, so this is for H, this for H, and then plus, then there are oxygen, there are only 1, but oxygen is 16, so 16 gram per mole times 1. So you will get 18 lah. So this for O. So you will get 18 gram per mole lah, gram per mole. Meaning that you know 18 gram of water is 1 mole. Okay? And 18 gram, if I ask you in terms of volume, because water, the density of water is 1. Okay, if this is in the mass, meaning that you give me 18 gram of water, then basically you know there is 1 mole of H2O lah. But if let's say I ask you, give me in terms of volume. Volume for water is ml, something like that lah. Okay, so because the density of water, density is basically mass over volume. Density of water is 1, and then the mass that you have is 18. So the volume is basically 18 ml lah. So it's more or less the same lah. That's why 18 gram of water more or less like 18 ml of water. But if you do that for oil or ethanol, it's different because density of the ethanol is different than water. Water, the density is 1. That's why you can say that 18 gram of water is equivalent to 18 milliliter of water. So that's the calculation. So what I did now is basically to familiarize yourself how to convert mole into gram into volume lah. So that's what the purpose here lah. Okay, now atomic mass unit. Just now some of you said that this mass is AMU. What is atomic mass unit? Okay, atomic mass unit is basically a mass of 1/12 of carbon 12. What does it mean is that what does it mean is that inside a carbon, you know, inside a carbon there are 6. You see the carbon, you see there the carbon. Inside the carbon there are 6 protons. So you have 1, 2, 3, 4, 5, 6 proton. 6 proton, and then there are 6 electron. So let's say there are 6 electron. 1, 2, 3, 4, 5, 6 electron. And then number of neutron we learned in the last class. Number of neutron and proton make up the mass, which is another 6 lah. This is neutron. 1, 2, 3, 4, 5, 6. So this is neutron. And then this is the proton, and then there are 6 electrons. Okay, of course the electron doesn't do in this orbital lah, but just for the sake of, because I want to focus only on the proton, okay, proton and neutron. So what does it mean by AMU? Is that mass of 1/12 of carbon 12. 1/12 of carbon 12. What does it mean by 12 there? Is that this thing? This thing. You see this thing? There are 12 things. So 1 AMU is basic. Remember, the weight, the mass of the proton and the neutron is almost the same. It's almost the same, the size in terms of mass. 1 unit, 1/12 of atom 12 is basically this lah. We take only 1. So this is 1 AMU. 1 AMU, meaning that they use this as a basis to sort of like to calculate the others unit lah. Sometimes you heard the word this. AMU, U, and Dalton. Sometimes you heard people say that 50 Dalton, 50 Dalton. What does it mean? That means is that the atom or whatever there is, they have 50 of this. 50 of that thing lah, 50 of that thing. 50 of that thing lah, whatever the thing is. Meaning that the weight is equivalent to as if you have like this thing, 1/12 of carbon times 50. That is 50 Dalton. Okay? So that's basically, that's why they say unit. The unit is the basis. For example, let's say this wall is made up from the brick. So the brick is the unit. Okay? So I can say this whole class is made up from the 1,000 unit brick. Like that. Same like this. Atomic mass unit. But of course, we are more familiar with the use of gram and so on. So people try to find how to relate this atomic mass unit, because remember, this mass, one thing, in reality, in reality, this one thing, the weight is 1.66 times 10 to the power of negative 27 kg. But of course, it's so small and it's so cumbersome to use that a lot of numbers in your calculation. So that's why people come with the term unit. Okay, instead of saying this, they say that is just the amount of atomic mass unit. But atomic mass unit is quite ambiguous. Not ambiguous, meaning that it's just like a brick lah, just now that I said, just one brick. It cannot sort of like convey the message when we want to deal with the everyday life. In everyday life, we use gram and so on. If you want to weight something, you weight with the gram, not this brick or whatever. So people try to find relationship between atomic mass unit and with the gram. So that's why come the Avogadro number. So Avogadro number or mole, Avogadro, this thing, let me, yeah. So this, you say that 12 AMU is not the same as 12 gram. But people try to sort of like want to find the relationship between AMU with the gram so that we can use in the everyday life lah. That's why they come up with the Avogadro constant. Avogadro constant allow relationship to be made. That's why you can see that this one, okay, for example here, the carbon, okay, if you look carbon here, it should have the mass of 12 AMU, right? Because there are 12 things. Remember, electron is so less, so ringan apa ringan? So light, comparable to this thing. So what make the atomic mass is basically the nucleus, not the electron. So we learn about the AMU. So carbon, if you look, carbon have 6 proton and 6 neutron. The AMU is 12 AMU. And then people try to find relationship with using the Avogadro number, which is 6.02 times 10 to the power of 23. Then they got what we call 12 gram per mole. 12 gram per mole. So they find this 12 AMU equivalent to 12 gram per mole. But then if you look here, the carbon here is not exact. It's not the whole number. By right, if they find the relationship between the AMU and the mole, they should be the same lah, because they want to find the relationship. But now, when it should be like this, 12 AMU should be equivalent to 12 gram per mole. But then, on periodic table, it's 12.011. It's not a whole number. Why is that? It's because, this thing, why numbers 12.0, why they are decimal there is because of the isotope. Because atoms of the same element have different number of neutrons. So how to deal with the isotope is that carbon, if you look there, there are 6 proton and 6 neutron. But there are another carbon, there are 6 proton. Number of proton is fixed because number of proton define the atomic number. 6 is carbon. Number of neutron can be different. So it can be 7, it can be 8, and so on. So if you look here, let me show here. Okay, let's go to Google lah, carbon. So let's go to carbon. Carbon. Carbon, Wikipedia. Make it bigger. Go down. So, go down. Kenapa tak naik? Ni saya tak suka lah. Okay, if you look here. Okay, there. Yang ni mana? Yes. Dari depan. Dari depan. Okay, dia ke depan. So, saya panggil orang belakang lah. Siapa nama you? Ira. Siapa Ira? Nampak? Nampak. Okay, so basically one pemadam. Okay, so if you look there are different type of carbon. There are not only one carbon. There are carbon, mana banyak sangat benda nak perang, tak payah ni. Itulah. So you see there are different type of carbon. This carbon 12, what does it mean here? If you have a number of element and then numbers on the left, so this is isotope. If you have numbers here, that is other thing lah. Okay, this is normally if you have numbers here, that is basically if you have number on top is normally the atomic number. Here normally the what we call the electron number. But if you have numbers next to the left, right, left of the carbon, this means the isotope. What does it mean there is that inside this carbon, there are 12 neutron. This is number of neutron, this one. This is number of neutron, not the proton. Proton for carbon is always 6. Okay? And now, this 12 is basically number of proton plus neutron. Okay? We know carbon is always 6 proton. So this is fixed. So this is fixed. Okay? So if you see there are 12, so meaning that if C12, so basically 6 proton plus 6 neutron. Carbon 13, what does it mean carbon 13 there? Meaning that there are 6 proton, the proton number must be fixed. Because that defines the atomic number, atomic number lah. But because there are 13 here, so you can calculate, this is 7 neutron. So there are carbon, not like that. There are extra neutron. So if there are like another neutron here, so there is carbon 13. Okay? But if you look here, the most carbon that you found in the Earth is carbon 12, because you see the abundancy is 98. So this meaning that it's stable. Stable. Meaning that it's not decay lah, it's not decay so fast and so on. So there are two isotopes of carbon that is stable, which is carbon 12, carbon 13. Okay? So the numbers 12.0 whatever the thing come from by taking into account this thing, abundancy and then the mass lah. For example there, you know that 98.9% is carbon 12. So if you put it, the 0.989 times with the what? With the 12, because that is basically the mass, plus with this 0.01 times with the 13, you will get what? 0.989 times 12 plus 0.011 times 13. What you got? What? 12.011. So if you look 12.011, that is basically there. You look carbon there, so that thing. So 12.011 here. Alamak. So this 12.011. So this 12.011, why they are decimal here? Because they take into account the abundancy. Remember, the 12 here is just, we call it AMU or mass lah. So we know that there are 98% of the stable carbon 12 isotope. So we need to combine with this lah, another stable isotope, then you get this number. So isotope, how to calculate the isotope is to take into account the abundancy. So any question on this? Okay. So that's why you see each of these things, they have what we call carbon, you have 12, and then you see chlorine, you have what we call this 35.45 and so on. You can try at home by going to Wikipedia and then calculate like this, the abundancy plus the what we call the total number of proton and neutron inside the any element lah. So that's basically the isotope. Okay, where is the? So that's the isotope. Mana? Oh ni bukan ni. Okay, so that is the isotope. So next, you see, we done with the what we call knowing the numbers, what the numbers mean in the periodic table. Now we want to look the periodic table in general, give the overview of the periodic table. So if you look the periodic table here, the row here we call period. So this is 5th period from rubidium to the xenon. So that is 5th period, and then 6th period, and then 7th period. There are only 7 periods of periodic table. That's what we call periodic table. And then the column here, we call it group lah. So this is group 1, group 2, group 16, and group 17, and so on. And then there are 118 elements to date. To date, there are 118 elements found. Okay, but you see this 118 or this one, whatever the thing, this is found, not found, it's synthesized in 2002, the latest one lah. So there are 118 elements, which is different kind of atom that is found and also synthesized, but only until 92. 92 is here. So this is uranium. What does it mean by naturally occurring? Mean that you can find it on Earth. You can find lah on Earth or in the universe whatsoever. Whatever the rest, after 93 and onward, is basically synthetically made. It's not natural. Okay, how people make this thing? Because we know, for example, uranium is 92, and then plutonium is 94. The difference is just in the nucleus there are two more proton. So basically, how they make plutonium? Because remember, plutonium is not natural. People made it. So how they make plutonium is basically to add more proton lah. So there are something about decay and radioactive happening here lah. So they use uranium, and then there are some decay, and then the neutron convert into the proton, and proton goes to making the nucleus and so on. So the idea is that the plutonium is heavier than uranium. The way how they do it, to add more proton lah, more proton. And how they do it, sometimes using radioactive decay lah. I mean that we not touch on that radioactive lah. But basically the idea is that they synthesize the thing. Okay, and also if you look here, up to 92, these two elements, technetium and promethium. If you look here, normally at the at the bottom here, carbon 12.011, right? They are decimal. But here you see they are not decimal, meaning that when you see a decimal there, meaning that they are stable isotope. They are natural lah, because they are abundancy. They have some relationship with abundancy. But if there is no decimal, meaning that you synthesize or whatever lah. That's why we don't talk about isotope when we go beyond the uranium. Because if you look here, I don't know whether you can see or not, but you can open the the periodic table here. If you go to here, uranium here, plutonium. If you see the plutonium here, they are 244 in the bracket. Meaning that they are no isotope, they are just synthesis, and that's it. There are no case of abundancy. But if you look at the thing, for example, palladium, they are isotope, because you know this decimal means there are certain palladium that is abundance, but have different neutron configuration inside the atom lah. Okay. So mana? Okay, so this thing. So up to 92, there are two elements which is not natural lah, technetium and also promethium. And from Neptunian until the whatever this organ seneson ni, it's also not natural, meaning that people synthesis it. Okay, the periodic table doesn't mean that everything is found naturally, only until 92. Okay, the rest is synthetically produced. Okay, and also the grouping. So you can see this periodic table. You can see most of the periodic table is metal. So this is metal, metal part, the one in the shaded red. Okay, this is metal. And then this is metalloid, somewhat metal, somewhat not metal. Okay, so this is metalloid, and this is non-metal. So if you want to divide the periodic table in terms of group like that, so we have a lot of metal, and then we have something in between, and this is non-metal. Okay, so that is basically the general idea about the periodic table. If you look here, alamak, kenapa macam tu? Tak tahulah. So if you look there, now we talk about the column. Okay, element in the same column tend to have similar chemical properties. What does it mean is that if this column 1 is explosive, then the rest of the column here also explosive. Okay, the reason for that is that all these have the same valence electron. So that's the reason why each column here, every column here, have similar number of valence electron. So that's why, and remember, chemical reaction is basically the movement of valence electron. That's all. That's why whatever in the same column have the same properties chemically. So the first column there, we call it alkali metal. Okay, that's basically the soft metal. The hydrogen there, can you see the era? Aminah ada Aminah? Ada Aminah sini? Tak ada. Nasha apa? Nasha ni. If you look, you can see right. Over there, can you see? Can you see this? Because they are just like that. Hope you can see lah. So here, the first group is basically alkali metal, but hydrogen here is anomaly, meaning that this hydrogen is gas, the rest is metal. Sometimes in the periodic table, you will see the hydrogen is detached from this. Sometimes the hydrogen, they have their own, what we call, they put up, meaning that they don't combine with this first group, sometimes in certain periodic table. But anyway, this hydrogen still have similar properties for whatever in this first group, because if you look, okay. So because if you look, the hydrogen have one, this hydrogen have one electron. All the rest in the column 1 also have one valence electron. So this valence electron here is easy to go out. Okay, so meaning that hydrogen can become hydrogen plus easily. Okay, so that is the thing lah. So that share with all the thing, all the other in this element. And all the metal, soft metal in the first group is fun to throw in lake. Meaning that if you have that metal, let's say I have a sodium metal, I throw in the water, it will explode. The reason for that is that if you have a sodium plus H2O, you get NaOH plus H2. Okay, if you balance the thing, because this there are 2 to whatever, you balance the thing, you get like this lah. You balance, you get something like this. Okay, so this what happened. The reaction happens when you throw the sodium into the water. You generate the H2. H2 is hydrogen gas. H is element. H2 is hydrogen gas. H2 is flammable, very flammable. So it's spontaneously ignite for this group. Okay, so that is why when you throw in water, it will explode. So that's why it's fun to throw. Have you do this in primary school? What about? Secondary. Okay, secondary school. Okay, so now we go to the next column. So next column we call it alkali earth metal. It's more or less same like the first group, but it's tamer than alkali metal. Meaning that if you throw in the water, it will not explode. Okay, it will sort of like, it will, because the hydrogen gas there, they will produce hydrogen gas also, but this hydrogen gas is not enough, it's not spontaneously ignite, like that lah. So it's more or less tamer lah than the alkali metal there over there. And then you have this what we call the big white portion of the periodic table. This is what we call transition metal. This is a workhorse of industry. All the metal that is famous, for example, the iron. This is iron. This iron, and no, this is not iron. This aluminium. Whatever this iron inside this, the iron. So we know that we use iron a lot in our life lah. So this is a transition metal. So most of the transition metal is relatively hard. Okay, relatively hard, keras, except for the mercury. In fact, the mercury is the only element inside the periodic table that is liquid. The rest is either solid or gas. This is solid, this is gas, and this is the only liquid in the periodic table in the room environment. Because periodic table, when you see periodic table, it's basically on the 25 degree lah. I mean that in the room temperature environment lah. So the mercury is the only liquid in the periodic table. Okay. Talking about the transition metal, this transition metal is relatively stable, meaning that if, for example, let's say our room, the gold, our room is gold, gold is stable. It's priced for this stability. You use the gold, people use gold because it will not corrode and so on. That's what we call stable lah. But there are some elements can oxidize slowly. For example, the ferrum here, the iron lah, rust, R-U-S-T, rust. So some element can oxidize slowly. During oxidation, the air come in, and then the ferrum, the iron here become rust. Okay, and here, if you look here, if you go here, if you count 45, 50, 51, 52, 53, 54, 55, 56, and suddenly 72. The reason for that is that this 57 is bottom here. Okay, in reality, your periodic table should be like this. Periodic table, this is periodic table that you normally see. The real periodic table is basically when you go here. When you go to, I put white, you see what happened to this. Okay, I go white. Okay, you see. So this is the actual periodic table. But then, it make the periodic table so wide, so it's impractical to use lah. I mean, the A4 paper cannot fit the thing, so that's why people just do like that. People do like this condensed version, because the reality is like this. For example, the barium 56, 57, 58, so it goes nicely lah. The number count goes nicely. But because it's too wide, then that's why people just do like that. So that's the reason only. Okay. If you look here, if you look at the bottom here, mana ni? If you look at the bottom here, this is what we call the rare earth metal. Okay, rare earth metal. But it's not really rare at all. Some of it is really abundant. For example, the cerium here, this Ce, cerium, is basically the 26th most abundant material on Earth. And this, what we call, the neodymium. Neodymium is normally used for the magnet, making the strong magnet. The neodymium magnet or neodymium here, the abundancy is more than the gold. Okay, so they are more neodymium than the gold. So even though they call it rare earth metal, it's not really rare. People say that the word rare is more towards, it's difficult to extract from the compound. Okay, and then here on the top here, you can see lanthanide. Lanthanide, I don't know how to pronounce, but the reason why they are lanthanide because the first element here is they call it lanthanium. So that's why the entire thing they call it lanthanides. Okay, the bottom one is actinides because the first one, as usual, is actinium. So the rest is actinide. All the actinides here is radioactive, where the most popular is uranium and plutonium. Okay, so that is the rare earth metal. Next, the ordinary metal. But most of the ordinary metal that you think normally in the transition, for example, when people talk about metal, people talk about the iron, aluminium, iron, and so on. So that's normally in the transition metal. But yeah, they give a name, whatever. Most metal people think ordinary is transition metal. But yeah, it's still metal. For example, aluminium. People make the aeroplane body with the aluminium and so on, right? So this also aluminium. Okay? And that is metal. That's what we see just now is a metal. Now, if you look here, there are metalloids. Something metal, something not metal. They have the properties in between. So somewhat metal, somewhat non-metal. So this is generally used in semiconductor industry. Okay, if you look here, what we call this sort of like violate the trend in periodic table. Normally, I said before, whatever in the column is the same, right? Is the same properties. But here, all these things have more or less the same properties, metalloid. So it's sort of like violate the periodic table rule. Okay, so chemistry is like that. It's so complicated in such a way that there are no such hard and fast rule. It's just a rule. Okay, when I say this element in the same column tend to have similar chemical properties, that's just a rule. But you see this metalloid sort of like violate that rule. It's not like a diagonal there. So that's chemistry lah. So this is just a rule. Remember, it's just a rule. Okay, that's metalloid. And then you have this non-metal part. You have the carbon, nitrogen, and so on. So this part, the upper triangle here, normally you found in organic material lah. For example, in your body, you have the carbon, nitrogen, oxygen, normally connected with the hydrogen. Okay, and then you have here, this is what we call the halogen column. The halogen is pretty nasty lah. It can react with everything. For example, the fluorine here can react with almost everything. Okay, because it's very reactive. But then when you combine, and also chlorine here, also nasty because people use chlorine gas in World War I. But if you combine this as a compound, for example, table salt is a sodium chloride. Sodium chloride is a table salt. Chloride plus sodium. It's just a table salt. It's not really dangerous, right? I mean, so normally when a compound, it becomes compound, is what we call, is stable lah. It can be fit to use in the domestic area lah. And then you have this noble gas. So it's inert, meaning that the valence shell is fully occupied lah. Fully occupied, meaning that it will not react with anything lah. It will not react with anything. So it's just alone by themselves. Okay. So that is some of the story about the group in the periodic table. So the trend, let's talk about the trend now. So electronegativity, most of you taking the chemistry before. Electronegativity means that the ability to attract electron. The more electronegative, meaning that the atom, the element can attract electron readily. For example, this fluorine is more electronegative than lithium. So that's what does it mean lah. So the trend is that the element become more electronegative here, meaning that it become more it has more ability to tarik electron, stealing the electron here. Chlorine stealing the electron, this thing. Okay? And also from bottom to top, increase in electronegativity. In fact, if you can see this here lah. If you go to whatever this thing, where is the properties? Macam mana nak tengok tu? Macam mana? Mana kat tepi dia? Hilang dah. Normally ada something here. Oh, here. So for example, let's say I go to electronegativity, electron affinity, the ability to attract the electron. If I click here, you can see here, it become more electronegative here lah. More electronegative over here. And so on. Electron affinity lah. Okay. And ni lah, this is electron affinity, this is electron this one. This one. So you can see it goes from bottom to top. So you can see the numbers here. You can see the numbers here. There are some numbers here. If you open this in your browser later on when you go back in your hostel, you will see there are numbers here. You can see the numbers here is less than here. For example, here, lithium here is 0 point something. But the chlorine here is 3 point something. So that is number of electronegative lah. The higher the number, the more electronegative. As you can see, the trend is going up to the right. So this is electronegativity. And also another trend is atomic size. We learned before that what we call the atomic size. Actually, there are something here because you see here. There are something here. Here, nampak? There are something. Actually, this they doesn't capture everything, but they are like arrow to the bottom, to the bottom. So basically, the atomic size in decrease from left to right. We discussed before why the gold have smaller radius than the whatever here, because of the more gold have more neutron, and more neutron in order to keep the nucleus stable. So because of the more neutron, and then it will sort of like attract the radius of the electron radius, and it becomes shrink. So that's why even though these have higher number of a higher number of neutron and proton in the nucleus, but it is smaller than here. Okay, because the ability to attract the electron due to a higher number of proton is the influence is much higher, making the entire shell of the atom shrink. So that's why the size decrease from here to here. Okay, and also increase from top to bottom. This is common lah, because why it's increased from top to bottom is because if you look at here, if I go to the properties, where is how to go to properties? Okay, for example here, you can see here, the top one, there are 1 electron, and then it become bigger. It become more, you see there are more. So this is like 5, so meaning that there are like 5 orbits, 1, 2, 3, 4, 5. So the down you go, the more orbital there are, so the bigger they are lah. So that's why the size become bigger from top to bottom, and also from here to here, from right to the left, from this to this. Okay, so that is basically the what we call the trend for ni lah. Okay, so you can see why bonding occurs. So we talk about the bonding. Now we will talk about the bonding a little bit. So first of all, why bonding occurs? Why bonding occurs? We know that atom normally not live alone. For example, if you see carbon atom, they are not being carbon like that. I mean alone. For example, oxygen. You know they are oxygen element, but in real life, you know they are oxygen 2. They are no O. They always oxygen is always O2. Okay, and also water. They always have what we call the combination with others, hydrogen and oxygen. Similarly, if you have carbon in the real life, they are not exist alone like this. They always have either is connected with another carbon or another element like H or whatever lah. So the question is why? Why they are not alone? Why they are not alone? Yeah, because they want to reach the stable electronic configuration. Because all the what we call all the element in the periodic table have a valence shell except for the noble gas. So meaning that if you look here, all noble gas are monoatomic. If you look here, this thing, If I go to the electron, where is the electron affinity? The electron, so I go to electron here. So if you look here, you see there are always the, what we call the, so this, they are always not filled lah. You see here, the thing. The helium is filled lah, because the helium here is bring from here. Okay, so you can see this is filled. Okay, and if you go to the other stuff, for example copper, so you can see they are unfilled. Nampak tak? Nampak. Okay, so you can see here they are unfilled electron. Okay, so if you go to here, they are unfilled electron here because one orbital can fill in 2 electron, and except for this noble gas lah. If you see the noble gas, everything is filled, perfectly filled. So we call it octet lah. So when it's perfectly filled, meaning that this can exist in monoatomic, meaning that you can see, for example, oxygen. For example, oxygen is always oxygen 2. But neon, if you look around, this can exist neon lah. They exist in monoatomic. We call it monoatomic. Monoatomic means that it exists as itself because it's so stable that it doesn't need a combination with others lah. Okay. But other stuff, for example O, if you look O here, if I put O there, you look that thing, so you can see O have 2 sort of like a 6 valence electron. So let's say I draw O here, so meaning that I just draw Lewis structure, 1, 2, 3, 4, 5, 6. Okay, so this Lewis structure, this O, so this is not yet octet, not yet octet. In order to be stable, you need to achieve octet configuration, meaning that the outer either 2 or 8. That is octet lah. So not the either 2, meaning that 2 is only for helium, but octet means that you need to fill the valence shell with the 8. So in order to, so this is not stable because the outer electron is not octet yet. So that's why they need to have another O here, another O to make the octet. Okay, so they need another O, so they will combine like this. They will combine, they will sort of share. This thing is share. Okay, so you get 1, 2, 3, 4, 5, 6, 9, 7, 8. So 8, and this also this what we call this oxygen here also 1, 2, 3, 4, 5, 6, 7, 8. Okay, so because of that, the O2 is basically the double bond. So it's a double bond. If you see nitrogen is triple bond. Okay, if you see the chlorine is single bond. Okay, the reason is how they share. They need to make sure it's 8. So that's inilah. So when you see O2, it's not O single bond, it's double bond. When you see N2, nitrogen gas is triple bond. When you see chlorine Cl2, is Cl, single bond. So how you know the single, double, triple is basically by fulfilling the octet. Okay, that is the covalent bond that we will discuss later lah. Okay, so now let me open here. Okay, so now the question is why octet? Why octet? Yes, you said before that octet is stable, but why octet? Because you know that this is what we call the orbital. You know each orbital can be filled by 2 electrons. So you have S, P, D, F. You know this is based on the Pauli exclusion principle we learned in last class. Each orbital can fit maximum 2 electrons. So S orbital can fit 2 electrons. The P orbital can fit 6 electrons maximum because 2, 2, 2. The D, 10. The F, 14 because you have 2 here, 2, 2, 2, 2, 2, 2. So 14 lah. The question here, why octet? Why 8? Because you see here, some can fill up to 14. Why they say octet? Why not? Because some orbital can fill up to 14. Even if you look here, if I go like this, there are like 32 there. Even 32 electrons in one orbital. Okay, there are 32, there are 18. But now, why octet? Why people always say octet, octet, octet? Why not 3-2 octet? 3-2 or whatever thing. Because octet is 8, right? So, but you know from the SPDF orbital, the D can fill up up to 10 electron, the F can fill up to 14 electron. But why the case of octet? Anyone? This bonus. Why octet? Why octet if there are some orbital you can fill up to 32 and so on? Why octet? Why they always say octet, octet, octet? Siapa? Siapa nak? This is apa tu? Bonus. Jasmine nak? Tahu? Okay, the reason why it's octet, people always say octet, 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 is because only S and P orbital can have valence electron. The word valence, outermost electron. What does it mean? If you look here, okay, this look carefully. Okay, if you look here, look at this thing. Let's say I go to magnesium. Look here, there are 2, meaning that the outermost is 2. Outermost is 2. Let's say I go to the next element, which is number 13, aluminium. Look what happened here. So I go to the aluminium. If I go to aluminium, you see the numbers 2 there, it become 3. I go to silicon, 4. And also you see there, here, this thing, you see this. If I go to the aluminium, look here, I go to aluminium, just fill another one, fill another one, fill another one. Okay, but now, if I go to the calcium here, number 20, and I want to go 21, you see this 2, right? If I click here, what you think will happen? What you think will happen? If I click, this is number 20, and I want to click number 21. What will happen to this electron here? It will become like that. You see, the outermost doesn't change. Doesn't change. Doesn't change. Doesn't change. Outermost doesn't change. But they change inside. You see? This. Once you go to gallium, then only then it goes to 3. The reason for that, if you look here, if you go to from calcium to the xanthium, whatever this thing, it will fill in this thing. It will fill in this 3D first. And 3D is lower energy level than 4p. Okay? Lower energy, because it's like this. 1 go to 2. 2 go to S go to 2p. And then 2p go to 3s. 3s go to 3p. 3p go to 4s. 4s go to 3D. 3D go out. Itu ada selang-selang sikit. It's not like so you see 4s, this is 4s, and then it goes 4s and then go to 3D. Even though the number is 3, but it's higher energy level than 4s here. Here, okay. So that's why here this, and if you look here, what we call the outermost is maintain 2. Okay, maintain 2 because why 2 is because of this 4s. The 4s, they are 2. Okay, it becomes octet when the 4s and 4p fill up. Okay, if you go further to gallium, you see. Okay, you can see now the electron is become 3 because there are 4s, 2 electron there, then 4p, there are 1 electron there, and then go up, and then click on ni. So meaning that only this, the S and the P can become the valence orbital lah. Okay, so that's the reason why we call octet. And because the S and P, the S only occupy 2, the P can occupy maximum 6. 6 plus 2, 8. So that's why the octet only, we call octet because only the S orbital and P orbital can become the valence orbital. The D and F cannot be the valence orbital. So that's what we call the reason for that lah. The reason for that. Only S and P orbital can have valence electron. Okay, so if the electron is not octet, if the electron in valence not octet, atom will do whatever they can to fulfill the octet. Okay, electron will do whatever they can. For example, if you look here, for example, if I go to carbon, okay, carbon, you have a boron here. If you see boron, the outermost, the valence shell has 3 electrons, not octet. So boron will always make compound with other thing, either with another boron or another element lah. They cannot exist alone like that. Except for the neon, argon, krypton, xenon, radon, they can exist alone by itself because they are already stable. They are already inert lah. So they are already stable. They are already octet. 2s fill, 2p also fill. So this they can stay by their own. So you can see neon. Even neon gas is Ne. It's not Ne2. It's Ne. Argon gas is argon, Er. There are no 2 or 3 whatever. And also it will not make any bond with other stuff. Okay, so that's the reason for that lah. And then so how the electron can fill up the octet? We know that most of the element in the periodic table is not have a valent electron. So how they want to fulfill the valency, meaning making the octet, is by either donate or steal. This is what we call ionic bond, meaning that they give or take the electron, or they can share electron locally, which is covalent bond. It's covalent bond, they share locally, or they share electron globally. This is a metallic bond lah, metallic bonding. Okay, so here we will talk about this later about ionic, covalent, metallic in more detail later lah. So ionic, covalent, and metallic, we call it primary bonding because it is chemical bonding. When I say the chemical bonding, when people talk about chemical bonding, what does it mean is that the bonding that occur because the electron move somewhere, move outside that atom or element. So when you donate, of course you move the electron, right? This atom they donate, meaning that some electron will move somewhere physically. Share electron, yeah, electron move lah in the another orbital. And then share electron globally, the difference between this I will discuss in the further detail later on. But I want to say that ionic, covalent, metallic is what we call primary bonding, the bonding that happens chemically due to the electron transfer or so on, transfer or sharing. Okay, and then you have this van der Waals. Van der Waals is a secondary bonding. It's a physical bonding, meaning that the electron is not moving out. It's still inside the atom. It's not moving. It's just what we call, it's there, but this secondary bonding, even though the electron is not moving, the existence of van der Waals can have influence on the compound or whatever substance that you have. We will talk about the van der Waals in the next class lah. In the next class. So I think that's it for today.